Welcome to our discussion today on understanding projectile motion. Today we'll talk about some basics of projectile motion. We'll talk about how to calculate the time it takes for certain things to happen. And we'll find that the time is really the key to everything else. If you know when things are going to happen, it's much easier to find out what's going on at those times. And then we'll find the maximum height, and then we'll figure out how to calculate the range of the object. So let's get started with some basics. Projectile motion has two directions of velocity to think about. So there's the vertical component and there's the horizontal component. The horizontal velocity remains constant because gravity does not pull the object either backwards or forward. It pulls it straight down, which won't speed it up forward or backwards. Now there will be a little bit of slowing down due to air resistance, but if we consider that to be negligible, which it typically is for most things traveling at normal speeds, then we can get pretty close with saying that it remains constant. Now the horizontal velocity and the time in the air are the only two things that determine how far the object travels. So the faster outward it's going, of course, the farther it's going to go given the same time. Now for vertical motion, the object's going to gain or lose about 10 meters per second every single second. And really the number is 9.81 meters per second every second. But we use 10 to make things a little easier with worksheets. And the starting vertical velocity is the only thing that determines two things, both how high the object will get and how long it will be in the air. So those two things are both determined by your starting velocity. And it's the only thing that determines it. So the faster up it starts out, the higher up it goes, and the longer it will be in the air. They're related. All right, so let's get started with the calculations. Time in the air and time to the highest point. Like I said before, knowing the time things are happening at makes using equations a lot more simple. So we'll always start here with trying to figure out what time things are happening at. So if we have an object that's launched like this, it's going to follow this track roughly along here. And let's say that we start out with a starting velocity along this route here. We'll make this line. And let's say our starting velocity is something like 46.2 meters per second at an angle of 60 degrees. Now our first thing to do is figure out how much speed that is, how much velocity that is in the horizontal direction and the vertical direction. Okay, so let me draw them first of all. So we can see from this drawing that this velocity is pointed to the side a little bit, but mostly pointed up. So our vertical velocity is going to be from here to here. That's our vertical component. And our horizontal component will be from here to about here. So lining up vertically here and vertically here. These two that I've drawn added together make this one. Okay, so I'll put the arrowheads on these guys so you see which way they're going. And now we need to just calculate these two sides. Now if this is 60 and the whole thing is 90, this has to be 30. So we've got 30 degrees. And this side that we're trying to get, let's call this velocity in the x direction. And it is adjacent to this angle. And we learned earlier that the adjacent is the overall velocity times the cosine of this angle because it's adjacent. If it had been opposite, it would have been this side, it would have been the sine of that angle. So V cosine of 60 degrees. That'll give us our V sub x. Let's finish that off real quick. V sub x is equal to V, which is 46.2, times the cosine of 60 degrees. When you do this in your calculator, you find that the answer is 23.1 meters per second. Now on this side, this is the angle of 30 degrees, and this side is also adjacent this angle. So V in the y, so there's V in the x, the horizontal, V in the y, the vertical, is equal to V cosine of 30 degrees. We plug numbers in and we say, hey, v sub y is equal to 46.2 meters per second times the cosine of 30 degrees. And we find out that v sub y is 40.0 meters per second. So we have a vertical speed here to start out with of 40 meters per second and a horizontal of 23.1 meters per second. And that was just using our trig functions to find that. Okay. Now we know that our velocity here is going to be losing, our object's going to be losing 10 meters per second every second. So to find the time in the air, we know that it's going to lose 10 meters per second every second. We can just use our equation that change in velocity is equal to the acceleration times the change in time. If we solve this for time, we divide both sides by acceleration. I'm going to flip the time to this side. Change in time is equal to the change in velocity divided by the acceleration. And here we know to the highest point that v sub y is going to equal 0 meters per second. That's the point where it starts coming back down again. Right? So at that point, our change in y, our change in velocity, I should say, is 40 meters per second. And it's going to be a negative 40 meters per second because we're losing that much. It's a negative change. And then divided by our negative 10 meters per second. The meters per second cancel, the second flips to the top, and we find that our delta t is equal to 4 seconds, just as we would have thought. By losing 10 meters per second, it will take 4 seconds. So time to the highest point is found by using this equation. So if it takes 4 seconds to go from here to up here, it will take an additional 4 seconds to fall back down. So our total time in air is equal to 8 seconds. So that's just doubling the time to the highest point. So those are our two key time numbers that we need. We need to know where our highest point's happening at, what time our highest point's happening at, and at what time we're going to be colliding with the ground again. Knowing that means we can calculate anything else we need. Okay. So since we have this drawing up, let's go ahead and add in a few more key things. So here, this point is happening at 4 seconds. This point is about 3 seconds, about 2 seconds, and about 1 second. So at each of these seconds, we can actually draw in what's happening to the velocities. Now, we said before that the horizontal velocity is constant. So I'm going to draw this horizontal velocity is still 23.1 meters per second. And it's constant. So it's going to be the same. 23.1 meters per second. 23.1 meters per second. And this one, 23.1 meters per second. It doesn't change. Let's add the other side real quick. So at 5 seconds, it should be the same height across this way. 6 seconds, 7 seconds, 8 seconds. Now again, these are all 23.1. Exact same velocity as before. Now the difference is that this goes from being 40 meters per second to only being 30 meters per second. Because again, gravity is meaning it's going to lose 10 meters per second every second. And now it's going to be only 20 meters per second. And now only 10 meters per second. And here it's 0 meters per second. And now the velocity is going to go from being positive. It's going to lose velocity. Now it's going to gain velocity. But it's going to gain it downward. And it's going to be a negative 10 meters per second. A negative 20 meters per second. A negative 30 meters per second. And this is going to extend all the way down and off. And that's a negative 40 meters per second. So here, horizontal stays constant. The vertical velocity starts out big, gets smaller, smaller, smaller. And then on the other side it gets bigger, but now in a negative direction. Okay, so that's our velocities and our times. Now let's solve for height. And solving for height, we need to know a few things. We'll write down our time. So we said here that time to the top is equal to 4.0 seconds. Time all the way over here is equal to 8.0 seconds. And we're trying to figure out how high does it get. Well, our height equation comes in here. Our accelerated height equation, we learned before that the height is equal to the initial velocity. And this time, the only thing that determines how high it gets is the vertical component of the velocity, not this one, not the horizontal, but just this amount determines it. So we're going to label this v initial in the y times time plus 1/2 the acceleration, and here again this is the acceleration in the y direction, the vertical acceleration, t squared. So our height equation is v initial in the y times time, so just like it was before, plus 1/2 at squared. So this is the equation we've had a lot of experience with before in the past, and we can use it to find the height at any point. So let's do that real quick for a couple heights. So again, we said that 1 second was roughly here, 2 was roughly here, 3 was here, 4, 5, 6, 7, and 8. Let's see how well this works. So h is equal to v initial in the y, which is 40 meters per second, times time, let's say at 1 second, plus 1/2 at squared. Let's actually plug numbers in for that real quick. 1/2 times 10 meters per second times 1 second squared. So we can, this should be negative, sorry. This is 1/2 10 is 5 times 1 squared is 5. So this one is 40 times 1 is 40 meters. Height is equal to 40 meters minus 5 meters, which is equal to 35 meters. Which isn't surprising because this is how much gravity makes you fall in a second. So we're 5 meters away from where we would have been. So right here, this one would be a height of 35 meters. Now as we go up, we know that this 40 meters is going to be 40 times 2. It's going to be 80 meters at 2 seconds. And this one's going to be the same thing we've been doing this whole time. So 20 meters will be the answer here. And then 80 minus 20 is going to give us 60 meter height. So here, this one, height is equal to 60 meters. And this is at 1 second, 2 seconds, 3 seconds. Height is equal to, in 3 seconds, it should be at 120 meters without gravity, minus the 45 that gravity changes, and that's going to equal 75 meters. Notice how it went up 35 meters, and then went up only 25 meters, and now it's going to 15 meters. It's going up and up less each time because it's slowing down. At 4 seconds, the height is going to be, of course, 160 meters without acceleration, minus excuse me, the 80 meters that gravity affects it, and that's going to be an 80 meter height. And that's our maximum time. So if we just wanted to find our solving for maximum height, we would have just done this one equation right here. And we would have just plugged in that one equation for 4 seconds, because that's where our maximum height is. Now on the way back down, we'll quickly see height is equal to 5 seconds. It should be at 200 meters. Minus what gravity does, 125 meters, equals 75 meters. And so this side, 75 meters. And the way back down, you'll see that these start mirroring each other. This one, we do the calculation, is going to be 60 meters. This one is going to be 35 meters. And this one back down to 0 meters. Right? So this is one way to do it. Once you know the maximum, the time to the top, you can simply plug it into the height equation. You find the maximum height of 80 meters, 4 seconds in there. You can also subsequently find the height at any point along the route just by plugging in a time into the equation to find it. Now, if you ever did this and it kicked out a negative height, all it's referring to is it's past this point. So if I were to put like time of 9 seconds in here, it would give me a large negative height, which means it's fallen off of a cliff below where it was launched from, and it's way down here, or it's dug into the ground, something crazy has happened. Although dug in the ground wouldn't work because the equation would fall apart. So now we've learned how to find how much time it takes for it to get to the highest point and to get to its ending point, right, when it collides with the ground. We've found how to use that time to find the maximum height it reaches, right, as well as to find the heights anywhere along the path. Now we're going to learn how to find the maximum range, so how far out it goes. Now remember, in this case, the only thing that matters is how far the horizontal component of velocity, so how far sideways, how fast sideways it's going, and how much time it has to go that way. We know that the entire time it's going to be moving 23.1 meters per second. The question now is, how many seconds does it have? And remember, we said time to the top was 4 seconds for this problem. Time to the bottom was 8 seconds. So it's going to have 8 seconds of sideways motion to get from here to here. So to find how far it goes, there's no acceleration, so we just use our equation for velocity. Velocity is equal to change in distance divided by a change in time. Here we're trying to solve for the change in distance, so how far we move. So we multiply both sides by change in time. The 2 times cancel out, and we get that the change in distance is equal to the change in time times the velocity. And this equation works because the velocity here is constant. If it was a changing velocity, we'd have to use the accelerated equation. Right? So I just plug numbers in. So change in distance is equal to 8 seconds total, right? I have that much time in the air, times a velocity of 23.1 meters per second. Put that in your calculator. And you get that the change in distance is equal to 185 meters. So from here to here, this distance is 185 meters. That's where it's going to land at. Now you could figure out how far it got along any part of this way. Instead of putting in 8 seconds, you could put in 4 seconds. And you could figure out this horizontal distance. And if you wanted to, you could put in 1 second and figure out this horizontal distance. But again, when we do this, we're figuring out horizontal distances, not heights or total distance or anything like that. It's horizontal, how far we are across from where we started. All right, well, that does it for our projectile motion discussion. I hope you've enjoyed it, and I'll see you soon in the future.